All right, so I apologize for those of you who did not take math this semester because they didn't want to get any math in, because you're getting math today, but it's not too bad. Today we're going to be talking about specifically the Madhava-Leibniz sequence for approximating pi, which sounds like a whole lot of advanced nonsense, right? But mainly what we're going to be learning is how to do a pattern using a for loop. That's today's focus, which is doing a numerical addition subtraction pattern using a for loop, and also just learning a bit of math history and just kind of math facts, I guess. This isn't really that bad. It's just that, how to say, when you see stuff like this, especially that part on the far right, like over here, that can look a bit scary to a lot of people, right? That's just the way it is. But really what we're doing is we're going to be learning a pattern, okay? So let's just talk about pi first so that we can all get onto the same page. You probably all have learned about pi at some point because you had to do geometry at some point, which means you had to do circles at some point. Pi is this ratio between the diameter and the circumference of a circle. The best way, and if that means nothing to you, I find that a great way to kind of that this diagram did a better job of explaining this to me than any math class ever did. Which is to say that we've got a circle with a diameter 1. Okay? And if we start at the center of 0 and just kind of unroll it, then the total unrolled length of that circle is pi. It stops unrolling at pi. Right? That's what we mean when it's the ratio between the diameter and the circumference of the circle. Make sense? So it's useful basically for saying, and we need to know this because if we want to make a circle yay big, we want to know how much material we need for the outside of that circle. Okay? Now, the difficulty is that, as you can see, pi is 3.1415926535897. It's a lot of numbers, right? And basically, this is because it's what we call an irrational number. Irrational numbers are kind of irritating because as it says, it cannot be expressed exactly as the ratio of two integers, meaning that a lot of numbers, you can just represent them as a fraction. Right? What do I mean by that? You've got right, we have a number of repeating numbers, like this one over here, 0.333333, right? We can, and that just goes on forever. But we can represent that as a fraction, right? We know this because we've plugged this into our calculators before. This is just a third, right? It is 1/3. So we can get something like that from a fraction. Make sense? However, pi is different. There are no two numbers here and here that we can place accordingly that's going to give us, there is no such x and y, so to speak, that gives us 3.14159 and gives us all the digits of pi. Those numbers just don't exist. It's one of a few irrational numbers. That means that we can't really, it also means it kind of goes on forever, which means that we cannot really get a good value, a perfect value of it. Fortunately, when we're building stuff, we don't need good, we need good enough, which is where approximations come in. So basically the idea here is what we need to do is just simply, if long as we're accurate to here, we're in pretty good shape for most of the things we're building. Okay? Heck, even here or here is pretty good for things we're building, right? So a lot of different civilizations and cultures have all come up with different ways to approximate pi. ancient Egyptians, some ancient Egyptologists have basically said the Egyptians used the fraction 22 over 7 to get 3.14. And notice it's supposed to be 159. That gives you 3.14, so it gets you this part correct. But this part's off. It's about 0.04% too much. And that's actually fine for a lot of building. Okay? Babylonians did 25 over 8. Let's see. Indians, the Mahabharata, let's see, offered approximation of 3. Shatapatha Brahmana gave 339 over 108, 3.1 rather than 14159. It's 3.14 thereabouts, close to that. In China, they had a number of really nifty approximations. Again, 355 over 113, which are pretty darn good for fractions. Again, they didn't need to be exact. They never needed to be exact. And we can see that those worked throughout time. Right here is the graph of time on the bottom, and then the number of digits of pi that we were able to calculate as time went on. And notice that this is what we call a logarithmic graph, where each tick of the graph, each horizontal bar, represents 10 times as much as the last one, just like the Richter scale for earthquakes. So here we're saying basically we go from 1 to 10 to 100 to 1,000 digits. And notice, like, for this amount of period, to the 1400 for about 2,000 years, it's perfectly fine to have just a few digits of pi calculated for building stuff that need to be circular, like wheels, right? Perfectly fine. And then, as people start doing mathematics kind of recreationally, we see those numbers go up. And then you'll never guess what caused this big jump, right? It's computers. Computers caused this big jump for us to be able to get all the way up to 10 to the 14th power by using various approximations of pi to figure out how more and more digits of pi. Kind of just every so often, somebody just, it's one of the ways to show off you have a very powerful computer to calculate more and more digits of pi. Okay? So, also, like, this isn't necessarily, it's hard to graph these things, especially because, as we're going to see, various cultures found various approximations at different times, and when you discover something, well, when you don't have electronic communication and nice ways to instantly translate stuff, it sometimes takes a couple of centuries for people to find out that you already did this work. It's one of those annoying features. So you'll find that a lot of times, it gets named after some English dude, and in reality, some other guy figured it out 300 years ago. Okay? So, let's see. So pi is pretty important because of that relationship with circles. And it is just, again, it's one of those things that we can really just, we'll calculate it a couple times this semester. Today, what we're going to do is we're going to work on an approximation that was called the Madhava-Leibniz series. Gottfried Wilhelm Leibniz was, not British dude, but instead a member of the Holy Roman Empire, which, if you know your history, was neither holy nor Roman nor an empire. Those are the best equivalent I can say. It's pre-Germany Germany. So that is completely wrong, but also close enough for us to work with here. Okay. Anyway, he did a number of. He's a very famous mathematician. It's named after him because he discovered it independently, and Madhava discovered it quite some earlier time ago in the 1300s, 1400s. Okay, so it's sometimes called the Madhava series, the Madhava-Leibniz series. But the idea here is that we're not calculating pi. We're calculating pi over 4, which can be used to count. So in the end, when we do all our work, we're going to multiply it by 4 and we get pi. That makes sense to everybody? So we're just going to take our answer and multiply by 4 to get our answer. And as I mentioned, we have this really complicated formula which has this sigma, which just basically says we're going to add and add and add this number as it goes up. But this is a really kind of formal mathematics way of writing this pattern, which you'll be able to predict how that works in just a second. And the pattern is 1 minus a third plus a fifth minus a seventh plus a ninth minus what? What's the next one? Minus an 11th, and then plus what? 13 minus a 15th. So we know, so it's actually a fairly straightforward series. What it is that we've got a pattern here which is minus, plus, minus, plus, minus, plus. It alternates from adding to subtracting. If we consider this as plus 0, we can say it goes add, subtract, add, subtract, and then this starts as 1 over 1. And then we also see the second part of the series that changes, which is the denominator. The numerator never changes. The number on top never changes. It's only the number on the bottom, and it always goes up by 2. It's always our odd numbers, right? So basically it's saying if we take these fractions, subtract a third, add a fifth, seventh, ninth, if we do that all the way to infinity, which you can never really hit, but this gets into stuff from Calculus 2, which are converging series. But basically the idea, if you were able to hit infinity with this, you would get pi over 4. Or for a more realistic kind of idea, the more of this pattern we complete, the more accurate this will be for pi over 4. Does that make sense? The more and more we do, the more accurate our result gets. Does that make sense? So this is why we call it an approximation of pi. And you're going to see this a lot if you take a number of classes with me, which is that I enjoy the fact that in a lot of times in mathematics, we can cheat. We don't actually have to do we don't actually have to do like hard equations sometimes. We can often do an estimation, and as long as the estimation is close enough, it works. There's like an entire mathematics course called numerical analysis that is dedicated towards, hey, those differential equations, those are hard. Let's instead just make the computer do the hard work and think about getting somewhere close. And as long as the error of our approximation is smaller than the error that the machine can hold, then nobody's going to be able to tell the difference on how you solved it. So these approximation algorithms are pretty good. This is an approximation of pi. Okay. So the question is, how do we go about solving this? Okay. The first thing we need to do is figure out a way to kind of automate this. Okay. And that's what we're going to get into today with our for loop. Okay. Because what we want to do is we really want to kind of go from one thing to another, right? The first thing we need to know is how can I continuously add things together to get a sum? Basically, how can I do it like this? So I can do 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1, right? I know that's boring, but I want to automate just adding 1 again and again and again until I get some number, right? Okay, so that's like our first step, which we'll learn how to do with our for loop. The second step is let's maybe figure out how to kind of do maybe 1 plus 2 plus 3 plus 4 plus 5, basically get it so that we're adding a different number each time. Make sense to everybody? Then we can try to do, well, rather than doing this, can we get 1 plus 1/2 plus a third? Or even better, can we figure out how we can, maybe even better start over here. So how do we skip numbers like this? Right? And the great thing is that vast majority of what we're going to be doing is doable with the pieces of the for loop that we know, with one exception, which is we're going to learn that part of the for loop I said was blank. So let's go ahead and start by learning about the for loop and what we can do with it. Okay. So to review from last time, Control S, desktop, for loop stuff. Okay, so last time I left off by saying, hey, here we have a for loop. For blank in, and I said basically a for loop has four parts. It has a for x in y. The x and the y change depending on whatever we're doing. But the for and the in and this colon afterwards never change, right? Those are always present. For the vast majority of stuff we're doing for the first week, this y is going to be not the first week, but these first few weeks is going to be the range. The vast majority of the stuff is going to be using this range, and we're going to learn all about range today, okay? And then this part's actually fairly easy. It's a variable. Basically, it's the name of something, the name of whatever is going to change, because a lot of times we want our for loop to change. I'll get to there in a second, but a lot of times we put in I for integer, because a lot of times what we're going to be asking is for an integer to change or an index to change. So a lot of times we use I. But for right now, we're going to back up and just simply go back to where we were, which is for, and let me lower the volume so I don't keep killing you with those dings. All right. For blank in range, and let's go do 5. So we can command the computer to do something a repeated number of times by doing this. Print world. Okay, and so we do hello world. We save it. We run it. Let's go ahead and set it up so we can make this a bit easier for us to see. So we see hello, 5 hellos, and a world. Why 5? Because I said 5 over here in the range. You can think of this form as saying repeat the thing we see in here 5 times. If I did taco instead of hello, it would print out taco 5 times. And if I did 10, it would do it 10 times. And if I did a lot, let's see, run module, save it, run. It would certainly try its best to do it a lot, but printing is slow. So if you ever find yourself in this situation where you accidentally made something go on for a very, very long time, you can hit Control-C or Command-C on the keyboard, or go over to here to the shell and hit Interrupt Execution, and it will just stop it. Okay? No shame in that. You don't have to basically wait in shame, okay, for it to correct itself. Okay? And for honestly, when we're doing something like this, for figuring out how many times it's going to run, whatever we put here, be it blank, be it I, we're back to 10. Let's go ahead and do 3 because we can see that. Be it blank, be it I, be it, let's see, super, taco, be it gobbledygook, that's not going to, whatever I put here is not going to change how many times this runs. All that determines how many times range runs is whatever we put inside range. Make sense? Now, what am I doing over here when I'm putting something over here? I'm creating a variable. So what we're going to do is we are going to, instead of maybe printing out this variable, and also I just want to emphasize this, the reason world didn't print out 3 times was because it was outside of the for loop. Taco is inside the for loop because it's indented inside of it, right? Taco, print, cat. Sorry, I just had to do this aside. Right, cat's going to print out taco cat, world, right? because that's inside the for loop. If this was outside the for loop, it would be taco, 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 cat world. Okay? So anyway, as I was saying, now that we've got established this is talking about how many times we're going to print something out, this variable, the for whatever, that whatever is going to be something that changes. Let's see how it changes by printing it out. 0, 1, 2. Let's go ahead and just simply get rid of that world and make it less complicated. 0, 1, 2. So if I put in range 3, it puts in 0, 1, 2. If I put in 10, it will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 9. Notice when I had 3, it printed out 3 separate numbers. And if we count 5, 10 numbers, right? It printed out 10 lines total. Make sense? So it still ran the same number of times. Let's go ahead and kind of just be a bit more specific about this. Print i's value is colon and space, and we don't need the space. Need the comma though. I's value is 0. I's value is 1, 2, 3, 4, 5. This part doesn't change because it's not a variable. It's the same thing printing out. So, when we say a variable, we mean it. It varies in value as we run through the for loop. What are those values? Well, it depends on what you throw into range. When we throw something into range, its values are from 0 up to, but not including the number we plugged in. We start counting at 0. Almost everything we do will start by counting at 0 when there's a range of numbers. So over here we've got, when we did, let's go ahead and do 5, shorten this up. We've got 0 up to, but not including 5. So 0, 1, 2, 3, 4. Make sense? So we go from 0 up to, but not including the number we put in. If I put in, let's go ahead and just kind of show you, I could put in n is equal to 5 over here for I in range n. So I can put a variable in here, no problem, right? And when we go run it, it goes, hey, what the heck is n's value? Oh, that's 5. So I'll run 5 times. 0, 1, 2, 3, 4. Okay. Cool. Now, before we continue on, let's talk about one of the tools that we'll be using a for loop for a whole lot in this class. And I mean a whole lot. And that is called the running sum. Now I'll be using the word total for this, but that's what we're doing. The running sum looks like this. Total is equal to 0. I'm just going to go ahead and go back to blank to minimize our fear. 5. Total is equal to total plus 1. Print total. A lot going on here, but the main thing to know is that this line over here is going to run 5 times. So before we do that, let's go ahead and just run this once to see what it does. Now I'm going to run this, but this is going to cause an error. An error that you'll see a lot. Doesn't even get the chance to run. We get something, it pops up and says, and I know it's hard to see because it's in my system dialog, it says unexpected indent. What's going on here is that in order to indent, you need the colon. The colon tells Python to expect indents, so if it sees something that's indented without a colon, it's like you're trying to put this code in something, but there's nothing to put it in. So we're going to uncomment that. So we have total is equal to 0. This line is commented out, so it's skipped. Then we have total is equal to total plus 1. Now remember, in math class, this would be basically you did something wrong with your calculations. But here, this is an operator. we are taking what's on the right side of the equation and storing it on the left. We compute what's on the right, store it in the box, in the variable on the left. It just so happens that the variable we are using is the same one we used over here. It could have been different, but it's not. Make sense? Just happens to be that same one. So here, we start with total is equal to 0. We do total, which is 0, plus 1. So 0 plus 1 is 1, right? And we store it, and so we compute that, and we just store it in total. And again, that just happens to be the spot that we were storing 0 in. And then we print out that value, so we get 1. Now, if we do this in a for loop 5 times, what we're going to do is we're going to basically do this. We're going to say total is equal to 0, and we're going to do the following 5 times. The first time, total is going to be equal to 0. Then we add 1 to it and store it in total. So total's value is now 1. Then with our second iteration through the loop, we take a look at total. Its value is 1. So we add 1 to it and store 2. Let's go ahead and print out what, let's go ahead and print this out, actually. Print total's current value, comma, total. Let's go ahead and open this up for a bit. We'll do a colon. Print total executing total is equal to total plus 1, which does, there's no variable, and I'm just saying we're doing this. And then and let's go ahead and basically say at start of iteration. Let's go at start at, let's go with that top. That makes sense topologically. Nah, before and after, that makes sense. I really put a lot of thought into this. Okay, anyway. Before and after. And if I run this, unfortunately, that goes pretty fast, and so we don't get to really digest it. So how can I slow it down for you guys with tools that we currently know? I'm going to do something a bit cheeky that I actually haven't thought of when teaching this class. I'm very happy that I thought about this. We're going to do an input here. Just a blank input. Why in the world am I doing that? Because inputs wait for you to basically hit the enter key, right? They wait for you to put in a message, and then you hit enter. So here, I'm not asking them for anything, and whatever I get from the user, I'm not going to be using it for anything, so I don't bother using an assignment statement. So what we're going to see is now, so total's current value before 0. I'm sorry. So at the beginning of this, total's current value is 0. Now we're going to execute total is equal to total plus 1. We execute it. Okay. Hit enter. Total's current value after is 1, right? 0 plus 1 is 1. Now we're at 1. Now we're going to execute total. We're at the start of our second iteration. Total plus 1 is equal to 2. So we're going to store 2 in there, and we get 2. Now we're at the start of our third iteration. Total plus 1 is 2 plus 1, which gives us 3. Then total is equal to total plus 1, which gives us 4. So we keep adding these values on and on and on. If you want to see this in action in more detail, or you need to visualize these things, okay? Again, I want to emphasize one of the cool things of our textbook is that this is kind of built in. You can go here, we can go 4, I know it's a bit hard to see, but 4 blank, let's go with 4, I'll just copy paste this code in actually. Copy, and I'll paste it just simply to speed up my time. I hit run, and yeah, I'm gonna get all this stuff here. Let's go ahead and remove these inputs from here because I'm not gonna need them for what I'm showing you. And if I instead hit show in code lens, you can see it as a pop-up here. I'll zoom out. You can see it as a pop-up window here, or you can go directly to this web page. Click the link to go directly to the web page, and what we'll see is that we can visualize the execution, where basically it says total is equal to 0. Total's value before is total. We are executing it. Total is equal to total plus 1, and notice that the total will change to 1. It also says this underscore is a variable, which technically it is, but so let's go ahead and play with that for a second. Okay. So we do this running sum. So we can add as many ones together as we can, and if we remove our lines over here, right, we're not going to deal with the print statements or the interrupting, and if we put in 1,000, 10,000 in fact, it's just going to spit out an answer because we're just adding 1 10,000 times, right? Make sense to everybody? So this variable changes each time because it exists outside of this for loop. Okay, so now the other thing we learned about is we have this value called I. So let's go ahead and I'm going to be deleting stuff left and right, so that's why, and this is like half the reason I record everything, okay? Because it's just, because the things I need are like slides. They aren't needed for the next kind of run. We're going to print out I, only I'm not going to do this. I'm going to do this up to 100, right? So to review, I in range, when we do I is going to take on the values for 0 up to but not including 100. Okay? And if I now undo a bunch of stuff over here and change this to I in range, and now if we put an I instead of a semicolon, if I do print I, right, nothing is going to change here except I'm printing out these numbers. And let me just make this more distinctive because we have this 100 after here, which can be confusing. So let's say it's total value is colon, comma, total. Just like that. Okay? So we go up to 0 through 99. That doesn't change the impact of these things at all. They're not interacting at all. Okay? Can you guess what I'm going to do now? I'm going to make them interact. Okay, let's go ahead and shrink this number down to make it less scary though. Right? Go to 5. 0, 1, 2, 3, 4. Total is 5. Because we're adding 1 each time. But what's the point of having a variable if you don't vary it? Total plus I, which will give us an interesting answer, which is 10. And if we do some math, 4 plus 3, that's 7. 1 plus 2 is 3. So the total of these 5 numbers is 10. We added 0. Then rather than adding 1, 1, 1, 1, 1, we added 0, 1, 2, 3, 4. All the 5 values of I. Does that make sense? I know that's like a bit of a big jump. But what we've gotten is that we've gone from this first point, 1 plus 1 plus 1 plus 1, to 1 plus 2 plus 3 plus 4 plus 5, only instead of being 1 plus 2 plus 3 plus 4 plus 5, because we start at 0, we're kind of here instead. Make sense? Again, maybe easier if we see it in the visualizer, which is this wonderful tool. Edit this code. Let's go ahead, and we don't need to print this out if we are currently just visualizing this. So total is, we set up total equal to 0. Now the red is going to execute. It says, hey, we're entering a for loop. We're setting up for I in range is 5. For I in range 5, which means that i's values are going to start at 0 and go up to, but not including, 5. So now we're going to execute this line. Total is equal to total plus I. So 0 is equal to 0 plus 0, in other words. Or total is equal to 0 plus 0, which becomes 0. So we execute that. And so we're done with that iteration of the loop. Now we go back to the top. We're saying, okay, it's for I in range 0 to 5. We just did 0. So we're going to do what now? We're going to do 1. So now our value is total plus 1. 0 plus 1. And there we go. Then i's value updates to 2. And we get total plus 2, total plus 3, total plus 4. And then we go back to the top and say, hey, are we done? Oh, it turns out we're done. So we exit the for loop and print out our total. So this is a very powerful tool for doing a running sum. And we'll come back to doing a running sum in a bit. But the running sum is something you're going to do often. Now, I'm sure a lot of you are starting to panic, wondering what in the world you're going to have to do on the exam and this kind of stuff on the exam. And I'm here to assure you a bit about the exam right now. So a lot of this first exam, the second exam, yes, you'll be writing plenty of code. And then I see that question being asked, when is the first exam? And the first exam is week 6, your sixth lab. This is currently week 3. Your lab 3 will be this Friday/Monday. So you've got a bit of time. So it'll be whenever lab 6 is for you, okay? So, but I know that this starts, but I know some students, and this can basically be, oh geez, we're getting serious now. So for the first exam, there's going to be a lot of, here's code, what is the output of it, right? There's a lot of that. Or in terms of turtles, here is some turtle code, please draw whatever is being executed. Or here is a drawing I have. Here's what I want to have. Please add to my code to finish the drawing. So not too much in the way of code writing, but a lot in the way of code reading. Okay, for this first exam. And you will be getting a practice exam around week 5. So, and a review session in class. So I do give you the tools. Okay. So, now we've got this for blank is blank. So we're going to forget about this running sum for a bit and just go back to what we can do with this, and then we're finally ready to start our question of going back to pi. So, for I in range. Now, turns out there's plenty of things we can do with this. There's actually a lot of things we can do with it. All we're concerning about ourselves with is range, and there's still plenty we can do more with range too. Because range seems kind of limited if we're always starting at 0, right? So we don't always have to start with 0. We can do something like this. 5, 10. Start at 5, go up to, but not include 10. In fact, anytime you put in one number, like we did earlier, 5, that's actually shorthand for this, 0 to 5. Make sense? So you can always specify, so range can take up to 3 arguments. If you just put in 1, that's the stopping point. Go up to, but not include this. If you put in 2, we're saying start at this point, go up to, but don't include this point. So here, 5, go up to, but don't include 10. 50, up to, but don't include 100. And let's go back to, again, I'm going to go ahead and go back to 5 and 10 for a sec. And part of the reason we start with 0, by the way, is to make this the question, answering the question of how many times will this print out a bit easier. Because to figure out how many times this is going to execute is very easy to calculate. All you do is take the stopping number and subtract the starting number. 10 minus 5, so it's going to print out 5 times. 5, 6, 7, 8, 9. 50 to 100, it's going to start at 50, go up to but not include 100, so it starts at, so we've got all the numbers 51 through 99, which is 49 numbers, and then we've got 50 itself, for a grand total of 50 numbers. So, it's very easy to figure that kind of thing out. Now, what about that third number? Surely that's something scary, and it can be sometimes, but I think you're going to be able to take a good guess as to what the output is going to be based off of me putting in the third number over here. 50, 110. Any guesses as to what our output is going to be? Anyone? Yes? Yes, it's going to go up by tens. The third, the variable is called the step variable, meaning it's going to tell us how big of how much we're going to be going up by. By default, when we go up by numbers, we're going up by ones, right? But nothing stops me from going up by twos or fours or 21s, I guess, right? And it's going to go up to, but not include that n number, right? Notice it goes up to 92, and we don't print out any numbers bigger than 100. So why am I bothered bringing this up? Because if I wanted to do all the odd numbers, I would just start at 1, go up to my stopping point, and go up by twos, right? For if we start at 1, we just simply and go up by twos, we get odd numbers. 1, 3, 5, right? Because we just keep going up by 2. If I start at 0 instead, I'm going to be going up like this. Now you can't leave off that first number. If you want to do that step, you're kind of stuck there. What happens if you do this? Well, it thinks you put in, I want to start at 100 and go up to but not include 0. Well, because that range doesn't have any numbers in it, it doesn't execute, right? The range 0 to 5 has 5 numbers in it, but the range 5 to 0 by counting up has no numbers in it, right? Now that being said, what if you did want to go from 5 down to, but not including 0? We can make the step negative to count down. Right? Makes sense. Right? And of course, if I do it like this, what happens if I do, but so that begs the question of what if I do 0 to 10, but counting down? And the answer is it's smart enough to know that's not going to work. Okay? Range is, so now before we start getting too worried, how often do we use these things? This is what I most oftenly, if you've got most of the time you'll just simply be saying, hey, for I in range, and giving the single value to what you want to go up to. Sometimes, as we'll see today, or the most next common thing I would say, is saying I want to go from 1 to the stop value and I want to include the stop value. See, I've added we were at 0, and we wanted to go up to, but not include the stop value. A lot of the times, if you want to do something, you'll do 1, and you want to include the stop value, so we'll go to stop plus 1, right? That's the next most common thing I'd say. And then maybe rarely you'll have a weird start and a weird stop. And then even rarer than that, you're going to have a weird start and a weird stop and a weird step. Okay. So the vast majority of the time, just one argument's going to do. So now that we have tools at our disposal, let's talk about how do we calculate this. So we need a running sum to calculate the following. Total is equal to 1 minus, let's go ahead and I'll just be explicit, 1 minus a third plus a fifth minus a seventh. And we're just going to do that for as long as we can, right? Or as long as the computer will let us. So, assuming I can, actually make it look legible, there's a reason I type everything. So like I said, this is a bit to get to. So instead what we're going to do is we are going to just build up progressively. Why are we going to just simply go to the end, straightforward to the end? So what we'll do is we'll first work on doing this running sum of adding 1 plus 2 plus 3 plus 4 plus 5. And now we're going to go doing it by odds. So first, let's set up a running sum. We're going to create two variables. Total is equal to 0. And I'm going to create our stopping point. Just basically say when we're going to stop, because I want you to get used to the fact that there can be a variable in here. Let's go with 100. Okay? So what we're going to do now is we are going to say, for I in range stop, we are going to print out, say, print, we're going to add total plus, and we'll add I over here. And then we'll do that over here. Total is equal to total plus I. We're not printing out total's value until the very end. Print total. But what we're doing now is that we're adding basically all these values up from 0 all the way up to, but not including 100. And if we do that, we get 4950. Okay, and I like to do this because I want to see what we're adding here. We can also just do start at 1, and let's go all the way to that stop. That's fine. Go up to but not including 100. We'll just skip the 0 because we're going to not need it. 1 plus 2 plus 3 plus 4 plus 5 all the way up to 100. And the reason why I do this is because now I want to only add odd numbers. So how do I do that? I use the third thing we learned, which is the step. To go 1, to go up by 2s. So we can go 1 to 3 to 5. Sorry, 1 to 3 to 5. If we do that, we get these values. Let's go ahead and make our stop a bit lower. 10. 1 plus 3 plus 5 plus 7 plus 9. So we can do something like, let's see. I'm trying to think. Let's see. We could do something like print out the current progress of what's about to execute by saying print, this is going to seem a bit weird, total plus I. Yeah, this is what we need to do. Total plus I is equal to, oh, this is a pain in the butt to write. Total plus I is equal to total plus I. So we're literally printing out the values of this equation, which is about to execute, right? We're printing out the current value of total, the current value of I, and their sum. What it will be when it executes. So we'll see that total's current value is 0. We're going to add 1, and we're going to get 1. Then, so notice we were going up by 1, 3, 5, 7, 9, right? So we get 1 is equal to 0 plus 1. Then we take 1, we take 1, add 3 to it, we get 4. We then take 4, add 5 to it, and we get 9. We take 9, add 7 to it, and we get 16. We take 16, add 9 to it, and we get 25, which is our final answer, because from 0 to 10, we're going, from 1 to 10, we're going up by 2s. So we are going up to, but not including 10. Right, once we hit past 10, we're going to stop. Does this make sense so far? Right? If I instead just had this and backtrack, right, we would be getting 1, where I've deleted going up by 2s. We'd start out with total is equal to 0, we'd add 1, and that's equal to 1. Then we'd take that 1, we'd add 2 to it, we'd get 3. We'd take the 3, add 3 to it, get 6. Take the 6, add 4 to it, get 10. Why are we adding 1, 2, 3, 4? Because i's value changes every line. Every line is a different execution of this loop, so it goes up 1, 2, 3, 4, 5, 6, 7, 8, 9. It goes up to, but does not include 10. Once we added this 2 in, we are going to go ahead and get this. 1, 3, 5, 7, 9. Now, let's go ahead and add in the fractions. Doing the turning it into a fraction, right? Okay, that's the next step, which is going here, which is 1 plus a third plus a fifth plus a seventh, and that's not nearly as hard as it seems, because all we're doing is putting a 1 on the on top of this, and that's, once you see it, you can't unsee it. All you have to do is just do this. 1 over the I, right? And let's print out to see what that looks like. So 1 over I, we got to change it to what we're doing over there. Total, and 1 over I. So we're going to be adding 1, 0 plus, so rather than doing 1, 3, 5, 7, 9, we see we have 1 and a bunch of repeating 3s, which is 1 plus a bunch of repeating 3s, which is a third, plus 0.2, which is a fifth, plus, does anybody actually have what a seventh is memorized? That's right, this is a bit hard to read. So let's take advantage of the fact that we're doing it like this, and what we'll do is we will print out 1 over I just do it like that because I know how the formatting is going to go. And we see we get, let's just zoom out here. Yes, the right side is going to be messy. Sorry, the left side of the equation is still going to be messy. But we get 1 plus a third, 1. Then we get 1.3 plus a fifth plus a seventh plus a ninth. And we see what's getting added there. Make sense? All right. So now all we have to do to get this calculation going with the for loop is we need to go from here to this. 1 minus a third plus a fifth minus a seventh plus a ninth, and so on and so forth. So the question is, how do we do that? Well, obviously we got to have a negative number in here somewhere. We need to do subtraction. Now, some of you who've already taken a programming class might be thinking, okay, so I guess this is when we learn if statements? And the answer is no. God, no. We're still learning for loops. Why would I introduce yet another block of code to indent into? No, no, no. We've got the tools to do this, which is math. Again, the idea here is that we want to start thinking of our operations not just as things that are used to do computations, but as tools, right? Just how like dividing by 10 or doing integer division by 10 can be used as a tool to cut off a number on the right side of a number, cut off a digit, right? What we've, if you've taken your algebra class, you've learned a rather interesting property when it comes to negative numbers, right? If you take some number that's like -5 and multiply it by -1, you get 5. We've learned that basically that by multiplying any number by -1, it's going to be the negative of that, and if it's a double negative, it becomes a positive, right? So what we need to do is that we basically need to sometimes have this number multiplied by -1 and sometimes not. And the easiest way to multiply by not -1 is to multiply by 1. If that makes sense, right? Multiplying by 1 effectively does nothing. So what we're going to do is I'm not going to change this plus. What I'm going to do over here is I'm going to add a variable called sign. And what we're going to do is we're going to multiply, and I'll use parentheses to make it plenty explicit. Doesn't really matter there, but I'm going to put it there. Sign times 1, and that sign sometimes it's going to be +1, and sometimes it's going to be -1. Basically, it's going to alternate between them. If I start out by just simply doing +1, right? Sign is equal to 1, right? For +1, right? Because remember, this is just +1. In fact, that's a completely valid operation I can do right there. It will recognize that as turn the number you're attached to positive. Then it doesn't change anything, right? Because it's the same as what we were doing. We just added a multiplication of 1 into here. Similarly, if I do -1, we're going to just start subtracting these numbers. And we can reflect this by adding, and the way we're going to need to reflect this, unfortunately, is by taking this plus, comma, and then it's going to be, I love doing this, sign. There we go. Sign times divide, boom, boom. And now we can see here that we've got a plus -3rd, plus a -5th, plus -7, plus -9. It keeps going down. So what we would like to do, we want this to start out as positive because our first thing we're going to do is we are going to add a 1. Then we need to subtract a 3rd. So how do I get it to subtract? Well, what I'm going to do is I'm going to take this sign and I'm going to flip-flop between it being positive and negative. The way I do that, and you'll see it, and again, it's one of those things that once you see it, it's a bit hard to unsee. Sign is equal to sign times -1. Because remember, multiplying something by -1 is going to change the sign of it, from negative to positive, or from positive to negative. So here, if we run this, you'll see it. We see 1 minus a third plus a fifth minus a seventh plus a ninth. Let's go ahead and actually simplify what we're printing out here, because it is getting messy with all those decimals. So let's go ahead and I'm going to just copy this. We don't need to see the total except at the end, so we're going to do just this bit. Sine divided by I. And so now what we're going to see is 1 minus a third plus a fifth minus a seventh plus a ninth. So we've got the sequence going, right? Now the question is this close to pi over 4? And the answer is, I don't have pi over 4 memorized. What do I look like? A math professor? No, I don't know pi over 4 memorized. So, and remember, this equation doesn't give us pi. It gives us pi over 4. So, but we've got it now, right? What we've got is we've got this print statement, which, and again, these print statements don't do anything but give information to the user, so they don't really do anything for us. So you're free to delete them. But basically we're saying, hey, our current total is going to be equal to, our new total is going to be equal to our current total plus whatever the sign of this is times 1 over the number we're currently on. So 1 over 3 or 5 or 7, right? And then the sign changes from positive to negative. We say we're going to take the current sign, multiply by -1. We're going to take that value and store it in here. And if you need to see this execute, again, I urge you to use the code tutor built into Runestone, or integrated in, rather. So the question is this actually a good representation of pi? So let's find out. Since the total is going to be pi over 4, let's go ahead and multiply by 4 to see how close this is. And the answer is 3.339682535. Not too close. We need to, this is an approximation. Like it said, the more of these we do, the closer we're going to get. So I'm going to do more. Let's do 100 of these. 3.1, and suddenly we see something interesting. I've said this a few times, 3.14159, but we got 3.12159. The 159 is there. Very interesting, but this isn't. So this is what's fascinating about the sequence, I find, which is that you get like a sequence of correct digits with one of them in the middle being wrong. So, and the interesting thing again is that the more of these we do, 3.13929, the more of these iterations we do, the more accurate it gets. Once we stop at adding -9999, we get 3.14139265359. Very close there. And then if I do this, let's go ahead and now mind you, you don't have to compute pi by yourself. Let's go ahead and do something I haven't done before. I'm going to go ahead and import math. Math has all those nasty math functions you love and hate, like sine and cosine and tangent. And most importantly, it has pi built into it, so we can figure out what it is. So let's go ahead and print out our total. Print out, and I always forget, is it math.pi lowercase? So yes, it is math.pi lowercase. Wait, does uppercase work too? I honestly don't know. I'll find out. No, it says, did you mean lowercase pi? Okay, cool. So we see here the real value of pi on top and the computed value of pi on the bottom. And then what we can do now is we can see how wrong our calculation is. How do we do that? We are going to print out their, I'll calculate their error by saying, hey, it's equal to math.pi minus total times 4 And yes, even though order of operations will make sure that's correct, I'm going to go ahead and put it in parentheses just to ensure it. Okay, and then right, very common mistake that was unforced on my part, which is that we do this computation, and it's not going to be worth anything if I don't give you that information. So it's saying it's 2 times the error between those two is equal to 2 times 10 to the negative 5th power, right? Goes into scientific notation there. So if we make our, if we go back to this being 10, we'll see that our error is much bigger. In fact, let's go ahead and any guesses as what abs does? No, it does not give our program muscles, unfortunately. It does not make it swole. Abs is short for absolute value. It will basically just simply removes that negative sign because error should not be negative or positive. It should just be the standard value. It doesn't have a direction. It's just an amount. So we can see that if we do it only a few times, it's off by this amount, which is it's off by basically 0.2, which we can find out actually what percentage of error that is by dividing. So that is 6% wrong. Make that more distinguishable. Let's go ahead and actually turn that into a readable value. Times 100, and then comma percent. Boop. So 6.3% off. And so if I go back to doing, let's say, if we go up to, not again, but 1,000,000, it's 6.3% off, which is pretty darn good. Oh, sorry, no, it's a 6.3 times 10 to the negative 5th percent off. It is very small percentage-wise. But interesting enough to know, if I hit run on this, notice that there was if I hit, I'm going to tell you when I hit my run key over here. Hit, run, boom, hit. But if I do it over for 1,000,000, hit, and now I'm going to hit OK, and you'll notice it just hangs just a little bit. Just a little pause. Now if I go to 10,000,000, a bit more of a significant pause there, right? In fact, I'm telling it to do 10 times as many numbers, so it takes 10 times as long to run. And then if I do another 10, it takes 10 times longer than that. Which is an annoyingly long time. So, but we can see we're getting, our amount of error is getting very small. You can see that here's pi, and we get a match all the way up through here, which is, remember, I had 3.14159 kind of as the value I memorized. So we have more than the number of digits I memorized correct. And for those of you coming from chemistry, that's 6 sig figs right there. That I had memorized, and this is getting 8 significant figures correct. So this is good up to 8 sig figs, which is a lot in chemistry, right?
Too much.
What?
Too many.
Too many, yeah. So this is what I mean by approximation algorithms being okay, because a lot of times you're going to be the error that you're getting is much less than the error your data has, right? We're going to be doing a lot of cheating at math later on. For instance, we're going to be figuring out games of chance, and playing games of chance, where basically you have a chance of getting a big payout, and rather than doing the statistical analysis of it, because Again, I think the prerequisite is what? College algebra for this class? Pre-algebra? Can't remember which is which. But the point being is that, like, I want to emphasize that a lot of times we can approach math problems from an alternate perspective. The way we'll end up, and that's like the last topic, the second to last big topic I covered in the class. It's called Monte Carlo approximations, which sounds really complicated, but all it's saying is rather than doing the hard math and statistical and probability and stuff like that, statistical analysis and probability, we're going to just play the game. We're going to have the computer play the game a couple million times for us, and then we're going to count the number of times it wins, and that will actually give us the percentage, something very close to the percentage of times we'll actually win. So it's very useful for those kind of things, especially when you get into kind of issues where the statistics just may not make sense at a first glance. Again, I know this, this is one of those things that starts out really easy at the beginning of this, and then I started throwing stuff out here. None of this stuff over here you really need to remember. So let's stop by summarizing what was important today. We've learned how to do a running total. Running sums are pretty good. You'll be using those in Lab 4. So don't worry if you didn't get it today. Running sums are what we need for Lab 4. We learned about the second part of the for statement, which is that we can have a variable here, and that changes. And then we learned about the three parts for the range. If we do it like this, i's values are from 0 up to, but not including the listed number, 10. If we do it like this, we have a start and stop point. Start at 5, go up to, but don't include 10. And then finally, if I have a number like this, it's going to go up by that amount. Common question I ask on the exam, or one of the questions I ask on the exam is something like this. Print out, what are the numbers that are printed out? Or what's the output of this program? In other words, what gets printed? And it'll be something like this. For I in range, and let's see. Because again, I can just put random numbers in there. 4, 30, and 8. Print I. And basically just asking you to do some... The math is never going to be terrible, right? This isn't... it isn't hard math per se, but, there's no shame in writing down your steps here. 4, add 8 to get 12. So we would do 4, 12, 20, 28. And that would be your output there. Okay? So, nothing wrong with, 4, 12, 20, 28. So that's the kind of question I typically ask. One of the questions I'll ask for on the exam for like 5 points. Okay? So that the difference is, it will look at, the only difference is that I'll just put in different numbers for there. And I'm not going to do, I promise you I'm not going to do something like this. Right? That's just silly. That being said, I am totally the professor who might do this. Right? And the output would be this doesn't, or I might do this, which is that it just prints out 2, because it starts at 2, it goes up by bleh, and once it's reached 2 plus bleh, it's gotten, we've stopped. Similarly, again, you will for sure have a question on the exam. Again, this is going quite on advanced. That looks something like this, which is, I think it would be like, something like this. What is the remainder of this number after being divided by 10? And the remainder of any number after being divided by 10 is its one place, which would be 4, right? So basically questions where you don't have to do the actual long division here. You know that the remainder is going to be 10, right? Make sense? Right. Again, this symbol means what is the remainder after division by 10, right? We divide, right? This is all going back to 4th grade. So we've learned our parts of our for loop. That will be a big deal to us in our lab 4 and 5. But you have time to hone those skills. For right now, practice on using the most basic form of the for loop, using the turtle, to kind of just make the repetition of it easier. All right, so I'm going to stop recording.